Good afternoon, everybody. For today, we have the honor of receiving Professor Ivan Jerman from National Institute of Chemistry from Slovenia. He's going to do honor for us today and present his work on concentrated solar covered absorber coatings, academic research and industrial application with a glimpse into aeronautical prospects. Professor Ivan Jerman is a senior researcher at the National Institute of Chemistry in Slovenia and the head of the Coating Development Lab. He graduated from the University of Ljubljana, Faculty of Education in 2005 and received a PhD from the University of Ljubljana, Faculty of Chemistry and Chemical Technology in 2009. He's interested in making polyhedral oligomeric gel, thin films, spectrally selective coating, finishing textile, surface treatment, and solar cells, flame retardant materials, and IR and Raman spectroscopy. He has authored more than 130 peer-reviewed scientific articles in global journals, and he has more than 2,500 citations. He has co-authored 9 patents, 2 of which have been sold to the German industry. He received 2 Innovation Awards in 2009, including the Pope Award for his invention, the use of nanocomposite for making paints for spectral selective coating for absorber in solar collectors. So thank you for presenting for us today, and you can start today.
Thank you for a very kind introduction.
You're welcome.
I'm really happy to be here at your center and giving a lecture to you. I learned a lot during those days. It was really fun for me and also a pleasure to be part of this project or program. So as we realize now, we will focus today on concentrated solar power. It's an important field. We know that we are asking for more and more renewable energy, so absorber coatings are part of technology which can be used for production of electricity. And I will present, let's say, the connection with the industry, our research, and maybe at the end, maybe some prospects, what could be done. So in the introduction, we all know I will do a short introduction about climate changing, current energy use, solar thermal, and then I will present research activities related to absorber coatings. It's a long way since we are working on solar absorber coating. We start, my mentor starts 30 years ago with solar absorber coatings, then the rest of the team is still active today. So I will present, let's say, activities nano level, pigment level, phase boundaries, surface treatment, and so on. At the end, maybe some benchmarking, and for sure, solar thermal roadmap at the end. So we are facing more and more that what we do in next 10 years will probably impact the new next few thousand years. I don't know if you agree with us. So quite often people are talking about the mass extinction. Many species are gone already now, and they say sometimes it depends from which perspective you are looking to the problem. Maybe it's a natural process, but we don't know. So there is a lot of publications about the risks, climate changing. We are facing a lot of problems, as we faced also a few weeks ago in Valencia, heavy rain and so on and so on. So we should do something to decrease the levels of let's say CO2, maybe renewable energies away. I learned yesterday at the aeronautical department that consumption of fuel is very low per person per 100 kilometers. It's even less than I consume when I'm driving to my work by car. alone, let's say. So I try to use shared cars with other colleagues. So this is a way for sure. So we all know that consumption is getting bigger and bigger, more and more energy is consumed. For sure, that's the reason why there is a big impact on climate. You all know that in the past a lot of energy was produced from coal, from oil, from gas. It's difficult to understand that maybe in China in last year they opened so many coal power plants that are currently running in Europe. So roughly the same amount which is running in Europe was newly opened in last year in China. So you imagine how much we impacted, let's say, the nature. So in addition to coal, oil, and gas, there is a small portion of renewable, more and more solar, wind, but we are facing the problems just because, you know, they are not stable source. You know, sun is shining just for a few hours, so storage is more and more important. But on the other side, electricity, we consume more and more. It's difficult to imagine for me as a chemist, maybe for you as a mechanic engineer. From this perspective, it's quite easy to understand that we are using about the same amount of energy for single charging of phone, like we are which energy could be used to dig the 100 kilo for 64 meters, something like this. So, you know, we really waste a lot of energy. And that's the reason why emissions are growing more and more by sector. So for sure, there are predictions what will be, you know, the Paris Agreement to decrease, but we are facing already that we are over 1.5 degrees, which is expected to be there at the end of the year. So electricity and heat are for sure, especially in my case, I'm coming from Slovenia. There is a cold winter, there is no sun, maybe no wind. Our country is not suitable for wind production. So we should transfer somehow energy from the summer to the winter, and also seasonal storage is important for us. But also for other northern countries where there's a lot of, it's a big population, we should produce electricity for heating, for heat pumps, and also most of the energy is used as a heat. So of course, the second most important is the industry, and transport is growing more and more. It's consuming a lot of energy. So how to produce clean energy, it's quite important. I calculate for myself, you see the map of CO2 emissions made by planes. That's the reason, you know, I thought for sure let's say 4 liters is not a lot per 100 kilometers, but I made a long journey from Slovenia, it's somewhere here, next to Italy, then to Frankfurt, and then to Portugal. I calculated that web page that for the both ways I will produce more than 500 kilograms of CO2, just me, you know. So I traveled last year to Australia, additional 1600 kilos, and so on and so on. That's the reason why the pollution is so high. So here maybe the global consumption. As I said before, there are nowadays the industry is a big consumer, the buildings a little bit in agriculture, and for sure the portion of energy it's mainly produced by more than 75% by fossil fuels, more and more. Yeah. So on the other side, there is a free energy. You know, this is a solar DNI irradiation map over the whole Europe, over the whole world. You see that the areas marked with the dark red are covered the so-called solar belt. You know, there are the countries they could extract a lot of energy from the sun. So especially a very good place is Chile. You know, the Atacama desert there. You know, normally people are interested to visit there. Really bright sky, I don't know, millions of stars at the night, just because the moisture is very low and there is no solar, let's say not solar, but light pollution. So, but on the other side, those places could extract a lot of solar energy. So activities on those places are already on the way. There are solar thermal, concentrated solar thermal power plants already there for mining industry. There are also in California. There are some in Morocco, in Israel, Australia. There are many in China, here in the desert, but also some in South Africa, really to collect enormous energy as a heat. So what are, let's say, what are the topics where we were active for 2 or 3 decades? So we were active in flat plate collectors, as I presented yesterday. We are, let's say, active in trough collectors. They are called trough collectors in last project, Frenchy, where we developed the black coating for the pipe. In that project, we developed black and other colors for flat plate collectors made out of polymeric materials. But we are also quite proud to be a part of development of coatings for concentrated solar power. It is a power plant with 50,000 mirrors. There is a tower in the middle, more than 250 meters tall. There is 1,000 square meters of absorber surface, and you reflect the solar light in the center on the tower, and you are producing here the heat, which is then used for production of steam, or you are using heat transfer media like molten salt to run the classical turbine at the bottom and producing the electricity. So I will focus today mainly on those coatings, just because you know, it's industrial application. You are using their high temperature. It's maybe connection with the aeronautic technology or stuff like this. So coatings should be stable at very high temperature. Could have some nice optical properties like high emission, low emission, or maybe high solar absorption, and so on. Even it's okay, I try to go back, but it doesn't work. So even 95 or even more than 95% of solar or visible light is absorbed. You see like a bright star from very far, you know. Still part of concentrated solar light is reflected. So that's the reason. So what is important? So it is important the amount of absorbed energy. It is important how much energy is reflected. Of course, it's important how the heat transfer is working. You know, if let's say our coatings have a good thermal conductivity in order to transfer the energy from the surface. So the people quite often describe that on the surface was a much higher temperature than inside, or the opposite, just because the heat transfer is decreasing with the time, and just because some, let's say, oxide layer is growing below. And then, as I said, you run the turbine at the bottom quite often in order to produce 24 hours electricity. There should be a really enormous storage tank with molten salt. Imagine, I don't know, 30,000 tons of molten salt at 320, 350 degree in order to fulfill the demands of the generator during 24 hours. So what is important for solar absorber coating, as I already mentioned, you know, the region wavelengths where the solar spectrum is. About 5% is in UV. Most of the energy is hidden in visible range, and then about 45% in the range of infrared. But in case of concentrated solar power plant, you know, also the emission or black body emission spectra is important, just because in case of low temperature, this wavelength of peak solar peak emission is much higher than in case of, let's say, high temperature, for instance, at, let's say, 1200 Kelvins, or if you have in contracts, let's say, 200 degrees C. So we are shifting more and more to sun temperature. And of course, as I said, we should absorb, so this is the green line is one of our coatings for low temperature application. As you could realize that it should have a really strong or low reflectance, about 96-97% should be absorbed, and in infrared region it should possess high reflectance. Just why? It's just when you have a high reflectance in infrared, it means that it emits a low amount of energy, so you are losing really small amount by radiation. For sure, you should fulfill the let's say the demand that you extract maximum what is possible in order that it is feasible or it works in the industry. So we calculate normally, or we do some calculation of figure of merit in order how our coatings should work, or how it's important at low temperature, with low concentration maybe, or with high concentration, how those values influence the coating. As you could see, there is much more important in case of inclination when you are dealing at high concentration and in contrast to low concentration. So our activities in order to optimize the coating were in the past really on all aspects. Just why? Just because let's say our contractor, Bright Source company, push us to the limit in order to fulfill all the demand. So the coating should have really high solar absorbance. Sometimes we didn't fulfill the demands of low thermal emittance. The cost of the coating was quite important. We should study the lifetime. We should study corrosion below and diffusion of elements, because when you are dealing with elements below from the substrate at 500 or 600 degrees, they diffuse inside the coating layer, influencing the crystal structure of the pigment, so the color is changing, so you absorb less light. Also, it should be stable in the desert region, maybe with some salt in air, corrosion stability. We work quite a lot with abrasion resistance, just because you could expect heavy sandstorms in the desert, and of course composition, roughness, uniformity is important, and so on. So what are the ways, you know, to prepare absorber coatings? You know, it's not a new phenomenon. People are thinking about the coatings already for decades. You know, they know if you are wearing black clothes, it is warm for you. It is the same here. You should prepare somehow the really dark coatings in order to collect the solar energy. So it could be done by spray coating, spray pyrolysis, dip coating, and so on, lithography, electroplating. But as I said, economic view is important. How to really apply a coating on let's say 1,000 square meter, or maybe how to produce the maintenance work up on the tower, on the ropes, and so on. So coatings should be low cost, should be easy to apply, should be somehow cured that it is like a lab at the end, and we tested a lot of different possibilities. Sure, some of those techniques are producing coatings really in the vacuum, under vacuum condition, and what you couldn't imagine that you produce, let's say, 20-meter long absorber, I don't know, heavy, few tons, and then you put in some vacuum chamber in order to apply, let's say, some special Kermet, double Kermet coating. So that's the reason why we decide for easy application, like a spray coating or spray coating. So, as I said, in order to absorb really main energy which is available, also the crystal structure of the pigment is important. So we studied with my PhD, Luka Notch, quite a lot during his PhD thesis, what is important, could we improve. So we studied the structure of the spinel structure, where normally those black pigments stable up to 1000 degrees or even more. You know, those pigments are quite often used also in glass in car. You know, on the top of the car there is a black shade in order to protect you, your view. So similar pigments are used here. They are composed of manganese, copper, and iron oxide, mixed oxide, and we tested different additions. We add different elements in order to change the structure. So to incorporate those somewhere in the spinel structure and to tune the optical properties. We do some modeling as well. So if in order to confirm if there are really at the end where are, let's say, we simulated the tear spectra in order to confirm if those dopants are on tetrahedral side or octahedral side, in order to really combine those results with measured, with experimental values, with infrared. As you could see, we get at the end good match in order to really model those interspecific doping on sites, you know, and we claim, okay, that's the reason why we get better absorption spectra at the end. So as I said, mainly related to really elemental level, nano level. As I told you already before, those things could change at high temperature with diffusion. So we observe quite often that if there is a diffusion from below inside the pigment structure, so high absorption is lost. So in the next step, I'm presenting what we do on pigment level. So as you could see here from, let's say, transmission electron measurements, you know, sometimes we try to modify the pigment particles just to protect the pigment against diffusion from other elements. So I was working quite a lot on polyhedral oligomeric sesquioxanes during my PhD. So we try to use them to put them on the surface. You could change or you could tune the pendant group on the smallest silica, which is known. It is octahedral system, eight silicon atoms in the corners connected over the oxygen bridge, and out of those corners you could apply different pendant groups. So some groups are responsible for let's say connection with the substrate, in this case a pigment particle. It is also important that pigments are well dispersed inside the paint in order to produce uniform layer to gain, let's say, high solar absorptivity. So as you could see here from the images from some publication, we do some mapping, EDS analysis, in addition to TEM measurements, transmission electron measurements. So we confirm that we could produce really tiny layer of silica on top of spinel particles. Those, let's say, that doping, if you call doping or surface modification, doesn't influence the the optical properties, but it protects the spinel against diffusion, let's say. A very tiny layer, our colleague measured about 1.5 nanometer, which is just a one layer of polyhedral oligomeric scissors dioxane cube is there. So in addition, you know, in case when you are dealing with oxidation protection of the substrate, we try also to use the same molecules to produce really monolayer of those molecules in order to protect the underlying substrate, to protect the diffusion of elements out of the surface. So we made a plasma treatment in order to increase the, let's say, reactive sites on the surface. Then we applied, for instance, epoxy, modified polyhedral oligomeric silicious dioxanes. We made a FTIR analysis in order to confirm that those silica molecules are there. In addition to XPS, we produce those layers by Langmuir blotted films. You know, the application where you put your molecules on top of water, for instance. You compress the stuff together in order to produce really dense film, and then you transform everything on the substrate. We cure, and as you could see, the thickness was very low. At the beginning it was mainly silica, and then after you could see the substrate like nickel, chromium, and so on, oxygen, which is low. For us, in this case, you know, quite often is a problem how to protect underlying layer against oxidation during curing, you know. So our coatings should be cured at quite high temperature in order to produce like ceramic or glass matrix, which is not porous, and in the meantime, when you are calcinating this structure, also the below-lying substrate is oxidizing. So we try to find a way how to protect under material to stop the oxidation. So one of the options is to cure the coating by laser. So in last period we worked quite a lot to cure the coating with laser. You know that laser could really heat up just a tiny layer in order to prevent the oxidation below. There was some collaboration with a Korean company. They produce on the top of the substrate really dense film of alumina, you know, like it is used for your screen on the phone in order to produce hard coating on the plastic. They were really very, very successful, you know, with the aerosol deposition. They produced such a dense coating that after 800 or few thousand hours at 800 degrees, there was no indication of the, let's say, oxidation. But the problem was that we couldn't add the black pigment because the properties of black pigment are not the same, and that was the main problem. So we tried to apply then in the second layer the let's say the black color, and for sure we faced the problems with adhesion and so on. So then we try to do also some modification of let's say additives for high temperature, maybe less, just because at 500 most of the carbon-based material in air atmosphere is burning out. But we published some, let's say, work where we modified the nanoplatelets graphene with different molecules in order to easy to incorporate, because quite often we are using for high temperature applications silicon-based binder, which is also sometimes maybe not a good host for the particles. So we try to modify with different molecules and to show at the end that we improve the dispersion. Then we work also in the anti-corrosion aspect. So when you add the platelet material inside, so the path for oxygen or water diffusion is increased. and therefore we improve, let's say, the corrosion resistance, let's say, for low temperature, thickness, sensitive spectral selective coating. So it was presented here in this. So, but as I mentioned already at the beginning, you know, the main problem for the company is, or to find the investor is, everyone is asking for how long, if we get, there will be a profit at the end or not. So we work quite hard on lifetime assessment, you know, just because let's say industrial partners set the goal, they say, okay, we would like to have a coating, we would like that you are testing our coatings. They say, okay, 95% of solar absorption is the limit, so when we could reach, but we would like to know this very fast, you know, we would like to know not in 20 years what will be the value for optical properties of the coating, we would like to know next year, because investors are in front of the house. We would like to calculate for how long and so on. So we try to mimic the same conditions like on field. We know what will be the weather there in the desert. We know for how many hours the sun is there. We know how many times turn on and turn off take place. So we know all those data, and we try to mimic this in lab. In case of low temperature coatings, you know, you could accelerate by increasing the temperature, but in case, for instance, if you heat aluminium maybe for 100 degrees more, from 100 to 200, there is no big changes in the material. But if you heat, for instance, Inconel with the limit at, let's say, 700, you couldn't heat up to, I don't know, 800 or 900 degrees to accelerate the degradation process. So we try to be sharp in the limits, and we try to accelerate maybe with addition of oxygen, with the morning dew, with cycle, with one speed, with second speed, and so on. And in the meantime, we test weekly solar absorptance, thermal emittance, and also mechanical properties like seed thickness, cracking, adhesion evaluation, and so on, in order to get a lot of data to produce the good foundation for modeling, you know. So as you could see here, we cut also quite often the coatings. We do lamellas out of these coatings after loading, and we evaluate how the chromium is moving inside the coating. So you could see here this is a image of the coating. We cut a small piece. So here below is the substrate made out of Inconel. Then on Inconel, oxide layer is formed just out of chromium oxide. This chromium oxide is often used as a protecting layer, and then those elements are diffusing inside the coating. So you see here the porous coating. You imagine that high amount of binder is sometimes evaporated, sometimes it is burnt out. So it's really difficult to produce dense coating for such a high temperature. So everything was then used for calculation. I don't plan to go in detail today how we do produce the model, but I will somehow describe the results. So as you could see, we couple isothermal load with cyclic load. So, but in addition, we evaluate just what happens with the coatings if we cycle them at different speed from room temperature up to 800. So we made in the 2-3 months few thousand cycles. We heat up, we cool down, we spray water inside the oven, and again, so we repeat. So at the end, we realized that the most damaging process is really cycling because of expansion and then movements, thermal expansion, which influence the solar absorptivity at the end. As I said at the beginning, solar absorptivity for them was very important, just because they would like to have 95%, more than 95%. So we we made a model, we put the threshold, and we reached the number that those high solar absorptivity coatings will be limited or will fulfill the demand about 95% of solar absorptivity in first 12 years. So then they decide if the coating should be maintained or replaced, or everything stay like this, and they try. So also other labs try to do the same research with different coatings. As I said, benchmarking is quite often also an issue. We often do the round-robin test, you know, different labs try to do the same in order to prove that, let's say, our evaluation was good, was correct, and so on. We were quite happy that we are also a part of the project where people try to benchmark, try to compare the coatings from different producers. As you could see, there were 12 coatings evaluated in the Raise Life project, and they compared. So we were quite happy that at the end it was presented once. We won the second place. So as the best one was provider here. So quite normally, or most often, people are using Pyromark 2500, which will be presented also more. It was made by for aeronautical or space application, but then it was just transformed to this field, and then also other coatings. So our coating with let's say maximum temperature 800 degrees, like external procedure, won the second. So, as I said, scale up was very important. Always, I realize also today that you are really really good or expert people here at this C-MAST Centrum, how to transfer or how to help the industry. So it was the same with us. At the beginning, we coat 3-ton absorber in Slovenia by spray coating, and then quite similar technology was used in Ashalim project in Israel. As you could see, nominal capacity is 121 megawatt. It was this operation started in 2019. There is 50,000 mirrors. Solar field area is about 1 million square meters, and so on. And yeah, it is running still today, providing the energy for this region. As you could see, there are also other power plants like this. So this was the first one made by BrightSource. It's an Ivanpah project in the United States. 3 towers where they are providing electrical energy for, I don't know, about 140,000 homes in this region. You know that this part of the United States is promoting a lot of renewable energy. Then there is a Nor Kurzet complex in Morocco, where there is also power. So the potential is big. So you know, the problem which people are facing, or researchers are facing, that the amount of paint which is used for this application is low, so you couldn't be rich at the end. Even, you know, it's much better that you develop the coating for wood, you sell large amount of wood coatings to Russia, but in this case, I don't know, you need only 1 ton per such a big project, which cost, I don't know, 1.5 billion euros and so on. So nobody likes to invest in research a lot. Quite often people like to use also to decrease the price of the electricity. We compete with the coal price, or price of electricity produced by coal. It's also very challenging. So the pipe materials below is quite often used with lower quality. So But as I said, we were active also on other fields. Solar heat for industrial processes is quite important. Friendship project I mentioned before. You know, you could see here from Absolicon. Absolicon is a Swedish company which is producing, was also part of the Friendship project, which is producing those draft collectors. You could see that with 1 megawatt you could save, I don't know, a lot of liters of oil, firewood, brown coal or gas, and you could feed that energy to the industry. You know that you need a lot of heat for textile production, paper production, and so on and so on. What we see today here, in order to optimize, to decrease the price, and so on. So, what are the targets of Europe you could see here from the IRENA web page, that we are planning to install 165 million square meter per year in order to fulfill the demands, what is needed to reach the level of CO2 in 2050. Maybe here are the data, what should be the solar thermal consumption by industry, and so on. So it's really challenging task for us, how to produce so much energy, how to produce so many square meters of absorbers, so how to produce, how to occupy a large amount of land for collecting solar energy. At the end, as I said, what is the maybe connection to our aeronautical prospects? As I said already before, similar like Pyromark, our coatings are formulated for protecting, decorating metallic surfaces which are exposed to extremely high temperatures. Coating could be used for space program, maybe some additional solar applications for oven with high temperature and so on. Our coating improve the heat transfer, infrared application, and due to the high emission, and we are developing also low solar emittance in some cases, so different activities are on the way. Maybe some camouflage coatings could be for, let's say, our joint activities, in order to really, because we are experienced in absorption, emission, we know how to tune those properties, and those, let's say, camouflage coatings could be on plain material like, or I don't know, trucks and many things, so metallic surfaces and so on. But in addition, we are equipped quite with a good, let's say, tools. I'm presenting here maybe high temperature emission measurements, which could be done at our institute. So there behind is a black body which emits up to 1200 degrees C. So we could compare when we put here the sample, so we heat again up to let's say 1000 degrees C or even more, and we compare what's the emission. So we could evaluate the emission at really high temperature, maybe additional at room temperature with spherical measurements. We could do some measurements which are maybe not so such, let's say, instruments are not at every corner. We invest in that equipment just because we expect we will do a lot of work maybe with the industry, concentrated solar power industry, but at the end we realize that they don't care about what are the values, they just count what they collect, how much the energy they produce. So during the last 10 years, or since 2013 time when I'm heading that group, a lot of people changed, only few you could recognize some faces. It's our technician, maybe it's also here in last image, and maybe some guys. This is my PhD student, Nigel from Belgium. This was his long time here in our group. So we try to be active on different fields. just because, you know, also in Slovenia, maybe in academics, we are not paid very well, so they found a better position somewhere in the industry. But I'm always happy that we offer them maybe good education, a lot of experience on different topics. And we are quite happy that at least 3 people are always helping us during this research. So Professor Franci Marzel is from theoretical department. He is modeling for us a lot of things, preparing the articles. Gregor Capone is really an excellent expert in SEM measurement with scanning electron microscope, and Francisco from also from our institute is expert for TEM measurement. So it was really, we always enjoyed the collaboration with them. And for sure, there was some funding from national research agency, European funds, Bright Source, as I mentioned, and so on. I believe our future is bright. We produce more and more renewable energy. Our air will be more clear, and our kids will be more and more happy. At the same moment, I am inviting you to Slovenia. I know it is not maybe a regular image. Even you are here from this nice part where some snow could be during the winter. I still remember cases like this with a lot of snow. It's not far. It's maybe 15 minutes drive from Ljubljana, 1500 meters above the sea. It's a very nice ski resort. It's not, let's say, normal case today, just because of global warming. We are producing also a lot of wine, tasty wine, so I didn't like to bring to a country like Portugal maybe some wine in order not to shame myself, but also really nice coastal region. This is Iran, here is Italy, this is our 30-kilometer coast. And then it's Croatia already, so they don't like it to give us the access to international waters, but who care? So we are happy. Very nice Bled Lake. So here is the airport somewhere here. When we flew to Frankfurt, I see the lake. It was daylight. It's presented on image. So we are located here. It was a long way, as I said. We produce a lot of CO2. And that's it. Thank you for your attention. If there are any questions, you are welcome.
Thank you so much.
Yeah.
So here, no, is there? No, it's perfect. It's okay. So this is a certificate from the research center, you know, for your presentation. It's a minimum that we can do.
Sure.
Yes. Thank you
It's
so much.
important for my grandkids. They will be happy to read.
Thank you so much.
Here. Thank you.
Once again, you know, thanks Professor Ivan for his very interesting presentation. I think
Yes, everything is for Professor Ivan.
Thank you.
you're welcome.
Thank you.
Yeah.